If we develop software, we have to think about how to arrange and store the data we are dealing with. The first step is to determine what kind of operations are performed on the data. That will lead you to the abstract data type you will need to use. An abstract data type describes a collection of data and the operations that can be performed on the data. The abstract data type includes the outcome of those operations, but it is not concerned about how these operations are performed. The data structure also describes a collection of data and the operations, but it also specifies how those operations work. Note that the data structure is independent of the programming language. We can implement the same data structure in different programming languages, like Java, C or Python, for example. In this tutorial, we explore two data structures, the array and the linked list. Then we learn about the abstract data types stack, queue, and DAG. Strictly speaking, the stack, queue, and DAG are abstract data types, but they are also often called data structures. The stack, queue, and DAG can be implemented using a linked list or an array. All data structures we introduce in this tutorial are linear, as the data is logically arranged in a linear fashion. One way to organize data is a list, like a shopping, mailing, or task list. Let's take for example a shopping list. The items in the list are arranged in a linear fashion. That means the items are listed sequentially, one after the other. A bookshelf arranges the books in a linear order as well. Or think about a folder with bills. The bills are placed in the folder, one after the other. There are other ways to arrange data. For example, we could arrange the shopping data in the form of a so-called tree, where we split the data into three parts: produce, dairy, and bakery. In this tutorial, we will study sequentially arranged data only. Let's develop an abstract data type for a shopping list. If I write a shopping list, I add new items at the end of the list. But I might remove an item at any position from the list. For example, I have added apples, oranges, and pears to my list, but then I decide that I won't eat so much fruit, so I cross out the oranges. Then continue adding. Sometimes I'm not sure whether I added already an item to my list, so I have to be able to determine whether, for example, bagels are already listed. In this case, bagels are not yet listed, so I add that item as well. When I'm in a store, I often skim over all items in the list to determine what to get next. Each time I place an item into the shopping cart, I cross it out. In the end, I need to be able to detect whether I've crossed out all items, that is, whether my list is empty. In summary, the list will keep track of a collection of items. I came up with the following 5 operations: add an item at the end of the list, remove an item at any position, check whether the list contains an item, check if the list is empty, display all items. Note that this is truly an abstract data type so far, since it does not specify how we implement the operations. There are 2 elementary data structures that can be used to implement the abstract data type list. There is the array and the linked list. Note that I like to call those linear data structures because they store data that is logically arranged in a linear fashion. However, that does not mean that the data is stored sequentially in memory. An array does store the data sequentially, but a linked list does not necessarily store its data sequentially in memory. We will introduce the array next. An array is a data structure that stores a collection of items of the same type. The items in an array are typically called elements. So we can use an array to store a sequence of integers or to store a list of, say, address objects. But the same array cannot store some integers and also some address objects. To understand how an array works, it is helpful to know how an array is stored in memory. When we create an array, a contiguous chunk of memory is reserved to be used for the array. We typically say that the memory is allocated. In most programming languages, you would specify how many elements will have to be stored in the array, and you would specify the type of the elements. For example, if we specify that we want to store 3 integers in an array, and assuming an integer requires 4 bytes, then 12 bytes would be allocated at creation of the array. In Java, we declare an integer array by first specifying the type of the elements in the array, like int for integers, then there are the opening and closing brackets, then the name of the array, say int array. Now this does only declare that the variable int array is an integer array, but it does not yet allocate any memory. To allocate memory, we write the following: int array equal new int, and then in brackets we specify the number of integers we can store in this array. So this line will reserve 12 consecutive bytes in memory to store up to 3 elements in our array. So how do we add, remove and access elements in an array? The elements in an array are numbered or indexed. In Java, the element at the first position has index 0. The second element has index 1, and so on. If we want to store the value 100 at index 0, we write int array at index 0 equal to 100. We don't have to fill the array from first to last element. We could store now the value 300 at index 2 and the value 200 at index 1. Similarly, if we want to access an element in an array, we use its index to access it. In this case, variable value will have the same value as int array at index 2, which is 300 in this case. Note that you can access any element at a given index position at any time in any order, even if you never stored an element at the requested position. You just need to know the index. That's why an array allows random access. Note that the index is a numeric type. We can also use an integer variable with an appropriate value as index in order to access or initialize an array element. Now let's remove an element from an array. Depending on what the result of a removal operation should be, the removal of an element can be cumbersome. Say you want to remove the element at index 0. In some cases, you may not have to explicitly remove the element, but you just don't need to access the element anymore. You can also replace the element at index 0 by another element. However, often all elements should be stored from left to right without a gap. Thus, if the first element is removed, all other elements should shift by one position to the left. We can use a for loop where we use the index as a counter. Note that in Java an array has a length field that allows us to determine the maximum number of elements that can be stored in an array. Therefore the for loop will terminate when the counter reaches the size of the array. In the first iteration, the element at index 0 is replaced by the element at index 1. In the second iteration, the element at index 1 is replaced by the element at index 2. It is important to note that the memory used by an array has to be contiguous. Let's say we need to store more than 3 integers, each requiring 4 bytes, but we have only allocated 12 bytes for the array. The memory that surrounds the 12 bytes for our array may be used already for other variables, for example. That's why the size of an array cannot be increased. An array is called a static data structure. Once the size has been determined in the beginning, we cannot increase it. Of course, what we can do is we can create a new array with a larger size, and then copy the content of the old array into the new larger array. Then we set int array to temp array, so we can continue working with int array and add more elements to it. In summary, an array is a data structure that stores a collection of elements with the same type sequentially in memory. An array allows random access. That means we can directly access an element at any position if we use its index. An array is static since its size is fixed when the array is created. As in the case of arrays, a linked list stores a collection of elements of the same type in sequential order. In a linked list, each element is wrapped in a container. The containers that wrap a list item are typically called nodes. The nodes might not be stored consecutively in memory. So in order to arrange the items of a linked list sequentially, the first node is marked, and each node points to the next one. That's where the name linked list comes from. The advantage of a linked list is that the size of the list grows and shrinks as new elements are added and removed respectively. We do not have to know in advance the maximum size of the linked list. If we want to add a new element, a new node is created and linked to the list. If an element is removed, the corresponding node is removed from the list by updating the links. Because the size of the linked list in memory grows and shrinks, a linked list is called a dynamic data structure. In order to implement a linked list in Java, we can create a node class. An object of the node class has to store the actual item in the list and a reference to the next item in the list. So the node class needs two fields, say a field called value and a field called next. For now we declare the value field to be of type object. This will allow us to store any type of object in the list. The next field should reference the next node and therefore is of type node. Here's an interesting observation. We have specified a class called node which has a field of the same type as its class itself. Now we can create a linked list class. The linked list class has to keep track of the first node in the list. The first node is also called the head of a linked list, so we add a field of type node called head. Note that we do not need to have more node fields. The head node will link to the second node, and the second node links to the third node, and so on. So by storing the head of the list, we can access all other elements in the linked list. However, if we want to access, say, the fourth element in the list, then we have to traverse the list starting at the head until we reach the fourth element. We cannot jump directly to the fourth element. That's why a linked list is called a sequential data structure. We have to traverse the elements sequentially to reach a particular element. Note that the node class is only used by the linked list. The user of a linked list should not be concerned about the node class. Indeed, the user of the linked list class should not have to know that such a class even exists. Therefore, we can place the node class into the linked list class as an inner class. This is about the simplest linked list class structure we could create in Java. It may be useful to add more fields to the class, like a size field. And of course, we need to add methods that allow to update and access elements. We can represent our simple list by a drawing where each node is a box and has a next pointer. A linked list can have a more complex structure. For example, a linked list can have a header, which is an additional node at the head of the list that does not contain an actual list item. It only serves to mark the beginning of the list. It also makes implementation of some list operations easier. In order to decide whether a node is the last node in the list, we can set the reference to the next node to null. Alternatively, we can insert a sentinel at the tail of the list, which, like a header node, is a node that does not contain a list item. Our simple list example has only single links that point from a node to the next node, so we can traverse the list from head to tail. In some cases, it might be useful to traverse the list from tail to head. In this case, we can use a doubly linked list. In a doubly linked list, each node has a reference to the previous and the next node in the list. All linked list implementations must be able to access the first node in a list. We can use a reference to the head, or if there's a header node, a reference to the header. In addition, we can also store a reference to the tail. Now let's look at a sample operation. Say we want to insert an item X, after the second item in the list. In the displayed list, there would be the position between item B and C. We create a new node and set its value to item X. Now we have to update the references to the next node to properly link the new node. Starting at the first node, we use a node reference to step through the list nodes until we have reached the node after which we want to insert the new node. We set the next pointer of the new node to reference a node with item C. And we set the next pointer of node to the new node. Now the new item has been inserted. In summary, a linked list is a data structure that stores a collection of elements with the same type logically in linear order. In order to access elements in a linked list, the list elements have to be traversed sequentially. A linked list is called a dynamic data structure since it grows and shrinks as elements are added and removed. We will learn about the three abstract data types stack, queue, and DAG. Recall that an abstract data type specifies what an operation accomplishes, but not how the operation should be performed. Okay, let's look first at the stack. A stack works like the displayed cup holder that stacks the cups. Our data items are represented by the cups. If we want to retrieve an item, we have to take it from the top of the stack. So we can only retrieve the items in the order in which they are placed on a stack from top to bottom. If we want to add items, we need to place them on the top of the stack. The basic stack operations are as follows. Determine whether stack is empty. Add an item to the stack. This operation is called push. We can say, for example, that an item is pushed onto the stack. Remove the item added most recently. This operation is called pop. So we may say an item is popped from the stack. Retrieve the item added most recently. This operation is often called peek. Since the item that is placed into a stack last is the one that is taken out first, the stack implements the so-called last in first out policy, or short LIFO. We trace a sample sequence of stack operations. The circle represents an empty stack. First, we push A onto the stack. Then we push another element B onto the stack. Now we push C onto the stack. Now we pop the most recently added element, which is C. Next we push D onto the stack. If we perform the pop operation, D will be popped from the stack. The peek operation returns B. The pop operation will remove B, and the last pop operation removes A. Note that the pop operation does not specify which element has to be removed, since the most recently added element always has to be removed. I've purposefully represented the stack as a circle without a particular arrangement of the elements in the stack, since the abstract data type stack does not prescribe how to structure the stack elements. However, it's much easier to trace the stack operations if we present the elements by an actual stack. So let's trace the same operations again. We push A, we push B onto the stack, and we push C onto the stack. Then we pop C from the stack, we push D on a stack, we pop D from the stack, the peek operation returns B, then we pop B from the stack, and finally we pop A from the stack. The important feature of stacks is that we add and remove items to, respectively, from a stack from the same end. The next abstract data type we look at is the queue. A queue works basically like a waiting line. We add items at the tail and remove items from the head. We can use a cup dispenser again to visualize its idea. In the displayed cup dispenser, cups can only be removed from the bottom, and new cups are added from the top. The basic queue operations are as follows. Determine whether queue is empty. Add an item to a queue. This operation is called inQueue. Remove the item that has been added least recently. This operation is called dQueue. Retrieve the item that has been added least recently without removing it, which is often called peek. Since the item that is placed into a queue first is the one that is taken out first, the queue implements a so-called first in, first out policy, or short FIFO. Let's trace a sequence of queue operations. The circle represents an empty queue. In queue A adds A to the queue. In queue B adds B to the queue. And in queue C adds C to the queue. The dequeue operation has to remove the item that has been added first, which is A. In queue D adds D, and the next dequeue operation removes B, since B has been added before C and D. Peek returns C without removing C from the queue. Dequeue removes C, since C has been added before D. And finally, dequeue removes the last item in the queue. Although the abstract data type queue does not specify that its elements need to be stored sequentially, it's much easier to trace the queue operations if we write down the elements from head to tail. We remove from the head and add new items at the tail. So let's trace the operations again. We in queue A, we in queue B, we in queue C, then dequeue removes A, we in queue D, dequeue removes B, peek returns C, dequeue removes C, and finally dequeue removes D. The last abstract data type we look at in this tutorial is the DAG, which is a short form for double-ended queue. The DAG allows to add items and remove items from both ends, but as in the case of the stack and queue, we cannot remove or add items in the middle of a DAG, for example. The DAG is specified by the following operations: determine whether a DAG is empty, add an item at the head, add an item at the tail, remove an item at the head, remove an item at the tail, retrieve an item at the head, retrieve an item at the tail. Let's trace a sequence of DAG operations. At head A adds the item A at the head of the DAG. At head B adds B at the head right in front of A. At tail C adds C at the tail behind A. Remove tail removes the item at the tail, which is C. At head D adds D in front of B at the head. Remove tail removes A, since A is now at the tail of the DAG. Get tail returns B. Remove head removes D. And finally remove head removes B. In summary, we have learned about 3 abstract data types. In all cases, we can imagine that the data is sequentially arranged. The stack requires to add and remove elements from the same end only. That end is typically called the top. In the queue, we add on one side the tail and remove from the opposite side, called the head. In the DAG, we can add at the head and at the tail, and remove from the head as well as the tail. Recall that a stack is an abstract data type, so it specifies the outcome of its operations. For example, the remove operation removes the element that has been added most recently, but it does not specify how we implement an operation. There are many ways to implement a stack. We will look at 2 ways: first a linked list implementation, and then an implementation that uses an array to store the stack items. Let's look at a sample sequence of operations on a stack. Say we insert the 3 items A, B, and C. Then we pop C from the stack, and then B. How do these operations work if we use a linked list? Let's use a singly linked list with a reference to the head of the list. Each item in the stack will become an item in the linked list. In the beginning, the stack is empty, so we start out with an empty list. We insert the first item, that is A. So the head references the first list node containing A. Where are we going to insert the next item, item B? Well, we will insert always at the head, so B goes before A. And then C is inserted at the head before B. The stack policy requires that we remove C in the upcoming pop operation, since C has been added most recently. We accomplish this by removing from the head, since the most recently added item is always at the head of the list. Finally, we pop B from the stack, that is, from the head of the linked list. In summary, the stack is represented by a linked list where each stack item is stored as a list item. All operations are performed at the head of the list. If we push an item onto the stack, it's added at the head of the linked list. If an item is popped from the stack, it's removed from the head of the list as well. The peek operation returns the item at the head of the linked list. And finally, the isEmpty operation checks whether the linked list is empty. A second common way to implement a stack is an array implementation. An array is used to store the items in the stack. Each item in the stack becomes an array element. Let's trace again the same sequence of stack operations as before to see how the array content changes. The push operations fill the array from left to right. Remember, in arrays, we need to know the index in order to insert an item. We will keep track of the size of the stack, that is the number of items in the stack. The size corresponds to the index of the position where the next item has to be inserted. In the beginning, the size is 0, and that is the index where we have to insert the first item, that is A in our example. After inserting A, the size is incremented by 1, so it's 1 now. Again, that is the index of the position where the second item, which is B, has to be inserted. Now the size has been incremented by 1, so it's 2. The third item is inserted at index 2. The pop operation has to remove item C. It is sufficient to decrement the size by 1. The second pop operation again decrements the size by 1, so the size now is 1. Note that we don't actually have to explicitly remove C and B from the array. So if we choose an array implementation, an array is used to hold all stack items. Items are inserted from left to right and removed from right to left. The size of the stack is stored in an additional variable. Basically, the variable stores the index of the top of the stack. The push operation adds an element at index size and increments size by 1. The pop operation decrements the size by 1. The peek operation returns the element at index size minus 1. This empty operation returns true if the size is 0. We will look at two ways to implement queues. The first implementation uses linked list, and the second one uses arrays. In case of the array implementation, we will see that the items in the array are arranged in a particular way that has led to the name circular array. Let's first trace a sample sequence of queue operations and then see how those operations work with a linked list. So we first insert the 3 items A, B, and C. Recall that we insert at the tail and remove from the head. So the next 2 dequeue operations remove A and then B. So how does the same sequence of operations work in a linked list? We use one linked list to store all queue items. In the beginning the queue is empty, so the linked list is empty as well. Now we insert A. We will always insert at the tail of the list so that the next item, which is item B, is inserted after A. Then C is inserted at the tail of the list. In the upcoming dequeue operation, we have to remove from the head to remove A. And finally B is removed from the head. In summary, all queue items are stored in a linked list. The inqueue operation adds at the tail of the list. The dequeue operation removes from the head of the list. The peek operation returns the item at the head of the list. Finally, the isEmpty operation returns true if the list is empty. Lastly, we look at the array implementation of a queue. We insert queue items from left to right into the array, starting at index 0. Let's say we insert A, B, C, and D. How do we know at which index to insert? Well, we need a variable that contains the index of the next position to be filled. we call the variable we use last. Last is really an integer type variable. In our scenario, last contains the value 4, since the next queue item has to be inserted at index 4. If we in-queue the additional item e, then last is incremented to 5 after inserting e at 4. When we in-queue f, f is inserted at index 5 and last is incremented to become 6. What happens if the dequeue operation is performed? The first item to be removed must be at index 0, since that is the position of the first item in the queue. Let's say we perform another dequeue operation. We need to keep track of the index of the element that has to be removed next, which is b at index 1. We use an additional integer variable that stores the index of the first element in the queue, that is the one at the head of the queue. So the dequeue operation removes b and increments first to become 2. The next dequeue operation removes c at index 2 and increments first to become 3. Now let's add more elements. There's no problem if we add g at index 6. Then we can add h at index 7. But note what happens to variable last. If we increment it by 1, it would be 8, which is an invalid index. What we do instead is we continue inserting at the beginning of the array at index 0. So the next item, item I, is inserted at 0, and last becomes 1. Item j is inserted at 1, and last becomes 2. If we continue inserting at the beginning of the array when we have reached the end, the array is called a circular array. Imagine that the fields of the array are arranged in a circular fashion, where the field of the last element touches the field of the first element. Now let's watch the same sequence of operations again. The elements are inserted and removed in clockwise order. Keep in mind though that we just use a normal array. So we insert A, B, C, D, E, and F. And now let's say we remove A, B, and C. Then we continue inserting G, H, I, and J. In summary, an array implementation of the queue stores all queue items as elements of an array. We use two variables, first and last, to keep track of the head and tail of the queue. First is the index of the position where the next item is removed, and last is the index where the next item is added. In turn, in-queue inserts at index last and increments last by 1. If variable last is equal to the array size, we need to set last to 0. The operation dequeue increments first by 1. Also here we have to set first to 0 if first is equal to the array size. Peek returns the item at index first. IsEmpty returns true if the variables first and last have the same value. So we have seen how linked lists and arrays can be used to implement stacks and queues respectively. In case of a linked list implementation of the stack, we need to add and remove from the head of the linked list. If we use an array for a stack, we need to keep track of the index of the top of the stack. In case of a linked list implementation of a queue, we add at the tail of the list and remove from the head. If we use an array, we keep track of the array index of the item at the head and of the item at the tail of the queue.